Hi everyone, this is Albert Lionel, and for this code along, we're going to code a simple hash table in C. It's not going to be a complete hash table, it's more just to get the ideas of what a hash table is. But let's follow along. As always, I encourage you, if any code along, you should open up your own IDE, you should follow along, you should pause the video, you can try it out, because the best way to do it is engage with the code, try it out yourself, and really see what is going on. Before we start too much into it, let's go ahead and take a look at what is a hash table, what makes it up, at least for this version of the hash table we're doing. There's a number of different versions you can look at. For this one, a hash table is an array and inside each element in that array, we actually have a node that is a key value pair. And if we need to store more than the size of this array, or we end up having to what we call a collision in our hashing function that causes us to store more, it also has a pointer to another node. So essentially, it is an array of singly linked lists. Now, ideally, these links are small. Ideally, we don't want this at all. So we hope that isn't there. We don't want to have it there. And we hope, hey, we only have one element in each spot, but occasionally you're going to have collisions, occasionally you're going to have multiple elements. But for this, we want to take a look at that one element. And as a reminder, we try to balance out, both based on our hashing function and the size of the table, on how we can ideally minimize there's only one element in each location. The advantage of doing this is, in practice, our axis ends up becoming O to the 1, a constant time, because we can instantly calculate and jump to any location in the array based on the key value that is being converted to a number, our hash. And so we're saying, here's my key may be a string, we're going to convert it using the hash, and we're going to mod it and get a location in this table. That gives us O of 1 access. And really, you end up with some collisions, so you may go out 2 or 3 or 4, but you don't go out a full size of the table, unless you have a really bad hashing function only returns 1 or 0 every time. But you only go out to the size of the table when you do it. So with that in mind, we'll go ahead and skip back over and we'll start taking a look at code and getting back into our code. Now, as a reminder, one of the other videos that we had before this was doing the DJB2 hash function. And this hash function basically starts at this 538 and ends up taking 538 and then multiplying it by 33 plus the constant value of this character string to get the number. We're going to use the same hash function. It's been copied over. You can grab the code. It was also in the previous video, so I encourage you to take a look at that previous video. So this has been drawn out. Instead of calling it DJB2, we just call it getHash in this case, just so it matches up. You'll see that I am doing this as an H file, so that means I've also created a C file that has a main that includes our H file, so that way, our header file, so that way we can go ahead and test what we're writing. And one of the first things you want to think about as a table is, what is our table size? So let's go ahead and just define that. I'm going to define size as, we'll say 1,000. It could be 100, it could be 5. We'll just go ahead and do 1,000. And then since we were saying that we have these nodes that we have to create, we'll go ahead and build that node. We're going to do type def struct. We'll do a node. And we'll go ahead and say tar star is our key, so that way we have strings for our key. In this case, we'll also go ahead and make our value a string. So we'll go ahead and say value. Let me go ahead and do some more of the C way of doing it. And then of course we have struct node next, because it's going to keep going down this node and keep going if we need to store more there. And I'll go ahead and do this as call this H node. So we have this, we have type def there, and to make my life easier, since your hash table is actually an array of these node pointers, since it's an array to all these different nodes, I'm going to go ahead and do type def and then H node star star. We'll call it hash table, the type hash table. So we have basically, anytime we pull up hash table, we're really actually pulling up this star star node for what we're doing. All right. Now, let's start off with a basic thing. Let's create the table. So when we create a table, we'll have hash table, create, and then we'll just return a hash table of malloc. Size of h node times star. Size, I mean. So we'll multiply it times size. So we've got this node, we're multiplying it by size so we can allocate it. And then whenever you create a free, it is really smart to go ahead and create a table. It's really smart to create a function, also freeze it. So void free table. And it's going to take in a hash table, TBL. Then I think about this, and before I can actually free the array, I'm going to have to free every node inside of it. And so we can say for int I equals 0, for I is less than size, I plus plus. Then we can free the node, right? Oh, not necessarily. And I'm going to go ahead and put in the free TBL just so we make sure we don't forget that at the end. And the reason why is because at every node, there's a potential that it is linked. It may not be linked, but there's a potential it's linked. So we couldn't just say free TBLI, because what would happen is that would freeze the first node, but the other nodes would still be sitting there in memory if there is more than one node due to the collision. So what we really will want to say is h node star current equals TBLI. Let's grab the current node. And while cur does not equal null, we're going to start looping. And based on our loop, then we're going to look at freeing things. So we can store it in a temp, because if we're releasing it, we probably should definitely grab the temp for the next. So we can say cur.next. And we can go ahead and say free cur now, and then cur equals temp. So that's sort of looping through every node, grabs the next one, stores it in a temp, frees the current one, takes a temp node, makes that the current, and keeps looping until it is null. And so that allows us to free every node and go from there. And so now I can create a table, we can free a table, and just to make sure that I don't have some weird, even though it'll be sort of hard to test at this point, we'll go ahead and do it. We'll say hash table, TBL equals create table. And then we'll go ahead and say free table, TBL. So I've got a table, I'm going to create it, I'm going to free it, and then I am going to compile and run just to make sure that I can go ahead and compile and run. So clang, and of course I have to compile, I'm going to put the walls here so if our warnings. Of course I have to compile the tests one. And we're going to do out, and we're just going to call table T for tests, or table tests dot out. Aha. I apologize. So I'm sitting here on Windows. Whenever I'm in Windows, I actually go into Linux. And before I started this video, I did not switch over to Linux. So I'm going to go ahead and start my Linux subsystem. And now let's go ahead and try that again. We have it. There we go. Now I can run hash out. All right. Not doing anything interesting at the moment, but it's created and it's freed. Theoretically, of course, there's nothing stored in it, so we'll get a better chance. But at least it compiles, and that's always a good step. Now let's go ahead and think about how do we add an item to this table. So we're going to do void add. And often you'll end up returning if the add is successful or not, but for now we're going to go ahead and do it as a void. And we need the table, so we're going to say, all right, hash table TBL, and then we need our char star for our key, and our char star for our value. We want to add a key and value. Now, one of the first things we want to do is we need to go ahead and get the hash value. So int hash equals, I need to change something, UL, there we go, equals get hash for the key mod size. First thing, let's go ahead and get the cache for there. We then say, all right, so we want to add this, and we also need to create the node. So let's go ahead and say hnode equals new node. Call it whatever you want, but that works. Let's say hnode star. malloc size of hnode. So we're basically creating this single node that we're going to take a look at, and we're mallocating, and then we need to store the values inside of it. So we can say new node key equals key, then new node value equals value, and then new node next equals null for now. So we have this sitting here where we have this key, we have the value, so we've created a node. Maybe I could have done this in a separate function, but for now we'll do it this way. And now we want to take a look at, all right, we've got this key. If my location, so if TBL hash equals null, then I know there's nothing in it. So I can just say, hey, TBL hash equals new node. And I'm done. Toss away. Don't worry about it. But what if there's a collision? What if we ended up creating something and we were like, all right, there's a collision and we need to sort of chain down this string? That's when I start thinking about my singly linked list. And so we want to say, all right, so we may have a node here. So we need to say hnode current equals TBL hash. Let's get the node that we're currently at. It's there. We know it's there because it does not equal null. Then we need to find the end of this chain. So we just need to loop grabbing the next until we have the end of the chain. Well, while cur next does not equal null, cur equals cur next. So what we're saying is for every node, we're going to keep looping down this node until we have a next that equals null, which means I have an empty spot in my chain. So I can say cur next equals new node. It's found the empty spot, it's inserted it. So that works there. So this is added it. Let's go and give it a try. So we need to come here and we're going to say, all right, let's go ahead and add TBL, and we're going to go ahead and call the key, let's say Princess Bride, and the value Buttercup. And then we'll say add TBL, and then we'll make the key Dread Pirate, Pirate Roberts, and we'll make the value Wesley. Now this is just going to add it. It's not going to tell us a huge amount because we're not printing anything out at this point, but at least we can add it. And we can go ahead and compile, make sure our compile does work, and we can run it. It seems to be running, seems to not be horribly crashing and seg faulting, so that's a good sign. What happens if I drop this table so I'm guaranteed to always have the same location? So we're now down to size 1. Let's go ahead and compile. There you run it. And it seems to be working without crashing. Let's go ahead and we'll increase that in a moment, but let's go ahead and make sure everything is there, that we are able to actually view it properly. So let's say void print table, and it takes in a hash table, TBL. The idea behind print table is we're going to basically cycle through making sure we can print everything in the table. To be nice is not required. I'm going to go ahead and put in a curly bracket at the beginning of this set. And then at the end, I'm going to go ahead and do a curly bracket just to say, hey, this is a table. Very used to how you may have seen dictionaries in Python. I'm trying to represent it the same way for doing that. And then I can say for int I equals 0, where I is less than size, I plus plus. And now we can start thinking about printing. However, hash tables don't necessarily start from 0 and you have every item filled. They can sort of skip around this array as they need. So I need to say, hey, if TBLI does not equal null, which means I actually have an element. So if it's null, I don't want to print null, obviously, so I'm going to go ahead and skip that. So we have if TBL equals I, we can say hCurrent, or hNode, current equals TBLI. Very similar to what we did above, grab the node that we're at. And while current doesn't equal null. Why? Because I'm curious in the current node, not the next one like I did in the add. I can say printf, %s, colon, %s, and we'll go ahead and pass in current key and current value. Then let's not forget to increment current, so current equals current next. And the moment this equals null, it's going to stop. Let's go ahead and run this. And someone who's looking at this saying, I'm missing something, that's sort of intentional. I want to run it so you can see a little bit though and make sure things don't crash. And then we forgot to actually call the print, which would be important. So let's go ahead and say print table TBL. So it works, except for there's no spacing. I want to make my life easier. I also only want, so I could say, hey, let's go ahead and add a comma to this. So you can say comma space at the front and try running this. Not really what I want because I have a comma at the space here, so I actually have to do a toggle. I also want to go ahead and add a \n here. So what I can say here is if print once. Has it printed once or not print once? Int print once equals 0, so it hasn't printed once. And then I can say if it has printed once, printf, comma space, allows me to get rid of this one here. Of course, remember semicolon. Then I can say if print once equals 0, print once equals 1. Hey, so the first time you've printed, don't print the comma when you're on the first item. After that, keep printing the comma with a space so I can nicely split up the items. But when it's the last item, it's not going to cycle through this again, so it's not going to add a comma necessarily at the end. So now I can go ahead and run this. I'm going to go ahead and clear this so it's easier to see. There we go. So it's nicely formatted. We have the key, Princess Bride. We have the value of Buttercup. We have Dread Pirate Roberts. We have the value of Wesley. And this is still on a table of size 1. So I can make this now size, we'll say 100. And it still works. So you notice my testing changes the size and say, hey, we have table size 1, which is really just a linked list when you do it at that point, but you're adding an extra table. Or size 100, which these are following in different locations. But these are things we can take a look at. Now let's work on getting an item. So we can add an item. We can print an item. Let's go ahead and get an item. So we have void get, it takes in the hash table TBL, and takes in the key. So we have a key, we have an item. Now let's go ahead and look at getting that item using it. First off, let's get our hash. I'll grab this line here, save myself from some typing. So we have this hash based on the size, and we convert it. We can then say, all right, if TBL hash equals null, we're going to return null. Why? Because item doesn't exist. I'm tossing in a key for something that doesn't exist in the table. And I apologize, it would not be void, it'd actually be car star. So it doesn't exist in the table, returns null saying, hey, it's not here. Else, we can say h node star current equals TBL hash. This seems like a very familiar pattern. And then while current does not equal null, so we're thinking more about the print patterns, we're interested in the current. Then we need to say, hey, we found this item, we found the hash. Now the hash isn't the same as the key. In the end, we still need to say, hey, we need to compare keys. To make our life easy, I did import the string library so we can use string compare, which what this does is it basically takes all the ASCII characters, adds them up together, and so if they're the same strings, it returns 0. So it is key, current key that we're comparing to key equals 0. We found it. We are going to return current value. And if that's not the case, so we haven't returned out of here, and by returning, by the way, this basically stops everything you're running, stops the loop right away. We can say current equals current next. Let's increment and go through there. But there's one other case I haven't really thought about. And I encourage you to pause the video and think about this case. So we've got the case where it doesn't exist, return null. We've got a case where something does exist based on here, and then we find the key and return it. What would be the third case? Take a moment to think about that, because there's another case that we're missing that we are going to have to put a return here. And maybe looking at the code, you're going to say, well, if I try doing this, it's not going to compile because it's missing a return, or at least I'll get a warning if I try compiling it. Let's see what happens. And what case is that really? Non-void function does not return a value at all control paths. So it's saying, hey, there is a situation here where return doesn't happen. And that's because return is based in this if statement. And so this else, there is a chance that something's not returned. So if we return null, and we do this, we lost that warning. By the way, this is why it is so important to have warnings enabled when you compile in C, because it would have let me run that, and there are cases where it could have had an error. And the reason why is, let's say we have a one-size table, and so you have only one spot, so every hash is going to drop down to that one. We store nothing in the table, and then we try to get a value. If we didn't have that null there, it wouldn't know what to do, because the key wouldn't actually exist, so it would have nothing compared to. Or we store an item, and there's only one thing, and we try to get a value of something else, actually. That would be more the case. So we store an item, we have this one size table, we didn't have that null there, and that is partially what causes issues. So this is sort of an important case to think about. But let's go ahead and run what we have. Actually, let's demonstrate this case. And let's go ahead and make this 1. So we're going to force a collision by making this 1. Then over here, we're going to say, all right, we're going to get TBL, and we're going to say man in black. So we have this, we're going to try getting the man in black. In fact, we're going to go ahead and print that. So we're going to say printf %s \n get man in black. Found, but not really. This is why it's important that we return null here, because we had a collision, but the key didn't actually exist. And now we can drop this back up to 100. We can go ahead and say printf Princess Bride is %s, and we can say get TBL Princess Bride. Who is a Princess Bride? Go ahead and return it. And let's add in the \n to make our life nicer. We'll see what happens when the null gets tried printing. There we go. So as you can see, this hash table can store things. It can go ahead and grab things based on a key value pair. And if you try to grab something that doesn't exist, null is returned. So there's a lot of things to take a look at, but overall, take your time with hash tables. The key to hash tables, no pun included, is really this whole section here, where you're sitting here going, I'm going to set the current, I'm going to loop through it. Or if I happen to find a collision, like over here in the add, I'm going to really look for the next so I can add that. So it is an array of these singly linked lists. Usually, in a perfect world, you don't have collisions, but collisions are going to exist, especially if your size of the table is too small. So test of different sizes. When you test with it, see if you can even calculate collisions. We could add a variable that calculates our collisions and then prints out how many collisions we're really having. Another fun thing to do would be to add a function that looks at the load factor, which looks at the number of items stored in the table, not necessarily the whole links, but the number of initial items, and divides it by the total number of tables. And you always want to keep your load factor pretty well balanced. So that is something to take into account. It would be a great function to help you explore it more. But as always, just code, keep coding, and happy coding. Have a great day. Thank you.